All right, let's start our lecture today. Welcome everybody, and I hope to see you every lecture. Okay. Now, I have sent an email to you yesterday. It's about the arrangement of the midterm exam. Now, due to the teaching schedule, we have a slight delay in our teaching, so I propose to postpone the midterm exam to the 10th of March, which is on Thursday. So we still have 2 weeks to go. That allows me to teach the topic of momentum and collision. And so after that, you have a week or two to review that topic. And for that topic, I think for momentum, I think I will only ask you simple fact questions because you haven't obtained the answer to the assignment yet, and so I will only test momentum, the chapter momentum for you on the simple questions. But for the other chapters, the syllabus is from chapter 1 to chapter 6. And for the other chapters, I will test you on the more difficult questions because you have already done the homework, right? Please read the regulation carefully. Now you are required to use a webcam to show your workings. Okay, show at least part of your face and also your handwriting on the paper. Now we are not accepting typing anything on the computer. You are not allowed to use iPad, tablet, all kinds of such device, because with such device you can easily communicate with the outside world with the internet. So I only allows you to use your mouse to control your computer, so you can view the exam paper, and I require you to handwrite your answer on a sheet of A4 paper. And after you finish writing on the paper, you finish answering the question on the paper, you are given at least 15 minutes to take photo of your answer and then upload it to the Blackboard. Okay. Now, if you find difficulty in doing that, the TA will help you. Okay. So don't worry. You have at least 15 minutes to do so. Okay. So the TA will make sure that every of you have submit the answer before letting you go. Okay, so if you find any difficulty, you just find the TA for help. I will be also around because you are divided into 2 groups, right? So I will be also around to help you if you have any problem. Okay, so I hope that arrangement will be fine for you. And if you have any doubt about the exam or about the regulation, please feel free to let me know. Okay, and you are also encouraged during the time of the examination. You are also encouraged to interact with us. You can go to the TA for help during the exercise class, or you can go to the consultation hours. The TA will be there at Zoom to cater for your individual question. So don't miss the chance. You have to wait. You have the chance to seek help from us, and we are all ready for help. Okay, so don't be shy in asking questions, because we are there to help you in your learning. Okay, and that is what I want to say. And I will also upload at least 2 past midterm paper for you to practice, and that will include also the solution. During these 2 weeks, I will upload the past paper for you to do some practice. And if you find any difficulty in doing it, if you find any difficulty in understanding the solution, you may ask us at any time you like. You just send us a message, and we may meet in Zoom, or I just answer you in the email. Okay, so I hope that will help you to do the exam. And please remember to stay safe during the pandemic time. I hope you good health for every of you. Don't get the COVID. Okay, so please stay safe in the pandemic. Okay. Now we're going to continue with our discussion on momentum, right? Now, remember in our previous lecture, what we told you is about a simple example of a force, external force, applying on a system with two masses, right? And we isolate each of the masses from the system, and we draw free body diagram for each, and then we come up with two equations of motion. But when we sum up the two equations of motion, we find that the internal force will cancel, okay? Because the internal force is the interaction force between M1 and M2. And when I sum up the two equations, the internal force will cancel, okay? And eventually, I find that the net force acting on the system as a whole is equal to the rate of change of the total momentum. Now, the total momentum is not the momentum of M1 or M2 alone. It is a sum of the momentum of M1 and M2. So it is P1 plus P2. So you see from this equation, this is called Newton's second law for a system of particles. And in this particular case, we only consider two particles. Sorry. Now I will answer the question about the exam during the break. Okay, you can type it in the chat box, but I don't want to disrupt the teaching. Okay, I'll answer it during the break. Okay, now you can see the internal force, the reaction force between the two masses, it would not affect the total momentum. Now the internal force play a role to transfer the momentum from one body to another. Now the interaction between the two bodies, it may some of the momentum from, because for example, if the two bodies collide, for example, then one body may transfer the momentum to another body via the internal force, via the normal force between the two bodies. Okay, but that will not decrease the total momentum, because one body loses the momentum, the other body will gain the momentum. So the total momentum will not be affected by the internal force. Okay, only the external force, as shown in this equation, only the external force will change the total momentum. And the external force acting on the system will be equal to the rate of change of the total momentum of the system. Okay, so is that clear? Now, so that means we have this equation, right? And remember, we can always extend our discussion to a general situation of n particle. And then in that situation, the total momentum will be the summation of the momentum of individual particle. Okay. So that is so-called the law of that is so-called the Newton's second law for a system of particle. Okay. We just replace the force acting on one particle by the force on the system, and we just replace the momentum of single particle by the total momentum of a system of particle. Okay. And in cases when the net force is zero, then the P dt is zero, and that means the total momentum is conserved. Okay. Now the individual momentum may change, but the sum of all the momentum of the particles always remains a constant in the absence of external force. That is the so-called the conservation of momentum. Okay. Now, having understand the idea, I would like to present a little bit more sophisticated mathematical formulation of what I just said to a system of n particle. Suppose now we have n particle, capital N. We have particle mass m1, m2, m3 up to mn. Okay, so we are going to study what is the force acting on the individual particle and also the system as a whole. Okay, now we consider particle mi, the mass with a mass mi. There are two kinds of force acting on it. The first kind of force denoted by this red arrow is the external force. The external force acting on particle I is called Fi with the superscript E. The superscript is just a sign to denote the external force, where I here is the subscript used to denote the force acting on particle I. Okay. Now, so this is the external force. For example, my hand, I may use my hand to disturb the system. That is from the external agent, okay? Like for example, my hand, okay? But there are also internal force, say between particle I and particle J, okay? Now we use a special notation, Fij, to denote the internal force. Now what is the meaning of Fij and Fji here? Fij, the first index means the particle pi I is under the action of the force. And the second index J means the particle J is responsible for producing this force. So Fij means the force acting on particle I due to particle J. And similarly, Fji means the particle acting on, means the force acting on particle J due to particle I. Okay, so Fij and Fji, they are a pair of action and reaction. They are due to the interaction of particle I and particle J. Okay, now we sum up all the forces acting on this particle. Okay, now this is the equation of motion for the I particle. This is the external force, and these are the internal force. Now you notice that there is a summation over J. Because the force acting on particle I may be due to all other particles, right? So that's why I sum up all the J. It may be due to particle 1, particle 2, or even particle n. So I form a summation of the force Fij over the index J. The index J is those particles who are producing force on particle I. Okay. So that forms the total force, and the total force on particle I is equal to the rate of change of momentum of particle I. And so that is the pi dt. Okay. Now let's form a second sum. Okay. Now particle I is just one of the particle. Okay. So it can stand for particle 1, particle 2, particle 3 up to particle n. So let's form a sum of all the forces acting on the particle. Okay, so I sum up the external force from I equal to 1 to n, and for the internal force, I also sum up the I from 1 to n. Okay, so I now add the second summation. Okay, and on the right hand side, I now form a summation of all the momentum of the particle from 1 to n. Okay, now so obviously, the right-hand side become the total momentum of the system, which I denote by capital P. Okay. Now, and then on the left-hand side, I find that the summation of Fie, because this is the external force, it becomes the total external force acting on all the particle. Okay, it is just a sum of all external force acting on the particle. Okay, so I denote it by the external force capital F. Okay. Now, the interesting thing is with this double sum. For this double sum, I have a sum of over Ij of Fij, right? Now, in this sum, I always encounter a term. For example, if I have a term Fij, I will always encounter another term called Fji. Now, take a particular example. If I and j both runs over 1 to n, then, for example, if I have come up with a term, which is F12, in this term, I is equal to 1 and j is equal to 2, right? I always will have this, will got this term, right? But I will also get another term in a sum. The other term is F21. In this term, I have I equal to 2 and j equal to 1. Right? And obviously they are a pair of action and reaction. So when they sum up together, because they are action and reaction, they are equal and opposite. And so these two terms sum up to 0. Okay, because they cancel each other, just like what we say about the two particles. The R cancel, the internal force cancel. Okay, now the interaction force between the particle I and particle J, they form an action-reaction pair to cancel. Okay, and similar thing will happen for the pair F, say F23 and F32 and F45 and F54. This pair of force will cancel each other. And so eventually, after doing the sum for all the particle, this double summation is equal to 0. So eventually, I would have the net force being equal to the total rate of change of the total momentum of the system. Okay, that is Newton's second law for a system of particle. Now I'm using a little bit more sophisticated notation. I hope the student with good mathematics will be able to comprehend. I also want you to accustom to this kind of more sophisticated notation when you are going to study more difficult physics in senior form. Okay, but I will not test you in examination. In examination, I will not use the difficult symbol. I only want you to understand the basic concept. Okay. Now we talk about collision. What is collision? A collision means a sharp impact between the two bodies. Okay, so that lasts for a very short time. Okay, by definition, what we mean by collision is that the two bodies interact with each other, but that happens in a relatively short time. Okay, and since this time is short, the collision force will be very large. Okay, and what we mean by very short time is it may last for as short as 1,000 of a second. It depends, of course, it depends on the problem that you are dealing with. For many of the collision may last only for 1,000 of a second or so. Okay. Now for a car crash is of course a collision. The collision time scale may be 100 of a second, several hundred of a second, about that order. Okay. A water droplet colliding with water surface, that is a collision. A golf cup and hitting a golf ball, that collision may be of the order, the duration may be of the order of 1,000 of a second. Okay, or maybe even the collision of celestial body. That is a collision, of course, but that may last much longer. Okay, because of a huge body. Okay. Now during the collision, the impact force, because the impact force is so large. Okay, so the impact force, the collision force, dominate over the other force. And so even if there are gravity, there are other kind of force, the effect will be negligible compared with the collision force. So during the very short moment of collision, the collision force dominate over all other force. So for the change in momentum that is caused by the collision, we only have to include the effect of the collision force. We can neglect the effect of the other force during that very short moment. Okay, so that is the idea of considering a collision. Now, how do we formulate the collision using the idea of momentum? Now, we first consider a body colliding with another body, and we consider change in momentum of the body dp in a small time interval dt. So Newton's second law say the little bit of change in momentum is due to the force of collision. Okay, and dp is equal to f dt if dt is sufficiently small, right? dt is the differential time. Okay, that is only Newton's second law. Now, of course, we would like to integrate this equation because we would like to know the total effect of the force, right? The force is changing with time. During the collision, the force will be increasing sharply with time, right? But that lasts for a very short moment. And a typical force profile will be coming like this. Now, Ti is the beginning of the collision, the time where the collision begins, and Tf is the time where the collision ends. And between these two times, the force may rise sharply to a very high value, and we will drop to 0. Okay, so that may be a very complicated profile for the force. Okay, now nobody will be able to measure it, or it's very difficult to measure because the time is very short. Okay, so in most of the situation we don't manage to measure the force precisely at different times. But we want to know the overall effect of the force during the time interval. And so we do an integration. We integrate both sides of this equation. And on the left-hand side, I assume that the initial momentum of the body is Pi and the final momentum is Pf. So the left-hand side will become the change in momentum, Pf minus Pi, okay? And the right-hand side will become the time integral of the force from the beginning to the end of the collision, okay? Now you notice that you have now had very special kind of integration of the integral of the force. Now, when we talk about energy, about work and energy, what we did is the integral of the force with respect to displacement. We integrate the force with respect to dx, and we find the work done, right? That is how we define work done, integrate the force with respect to displacement. But now, when we talk about momentum, there's another kind of integral of the force. We integrate the force over time instead of displacement. And the integral of the force over time is known as impulse. That is a technical name for integrating the force over time. Now, if we write this integral as J, then this equation says the change in momentum of body is equal to the impulse. Okay. Now, there's a graphical representation of the meaning of impulse. Consider one-dimensional motion. Here, F is plotted against T. The F may change in a very complicated profile, but we can always calculate the integral of F, and that becomes the area bounded below by the Ft curve. When I integrate F over T, what I get is the area bounded below by the impulse, the force profile. Okay, so I represent this area by the impulse. In some situation, it may be useful to talk about the average force. Okay, because the real force is very complicated. Okay, I do not know how to represent it. So I come up with a concept of using an average force to represent the effect of this force. Okay, now how to define the average force? We define the average force in the same time interval as a real force. If the real force starts from Ti and ends Tf, then the average force also starts from Ti and ends with Tf. Okay, but I define it such that the force, average force, is a constant during this time interval, and I call this F average. Okay. And so if I have a constant force, then the impulse due to this force will simply be the force magnitude multiplied by delta T, which is the area of the rectangle here. And I define the average force in such a way that the impulse due to this average force is exactly due to the impulse of the real force. So these two areas, the green area shown here, are equal. That is how we define the average force. So in other words, the impulse due to the average force is equal to the impulse due to the real force. But of course, for real force, we have to do the integral. And so I divide the whole equation by delta T. I find that the average force is the impulse delivered by the real force divided by the time interval of the collision. Okay. Now, so we have this equation. Okay. The impulse is the change in momentum, and that can be represented by the average force multiplied by the time interval. Now, so if I move the delta T to the left-hand side, I can easily see that the average force is inversely proportional to the duration of the collision. So for the same change in momentum, when the duration of collision is short, the average force will be very large. And that exactly is what you learn in high school, right? When the collision duration is short, the force will be huge. If the duration of the collision is lengthened, the force will be smaller. Okay, that is the idea you learn in high school. And this is exactly why you wear boxing gloves when you play boxing, because you don't want to harm others. And the boxing glove have a layer of cushion that allows the collision to happen more gently. Okay, and it's effectively lengthen the collision time, because it's compressing the cushion is compressing slowly. So it lengthens the collision time. It lengthens the time delta t, and that leads to a smaller collision force. Okay. And also, I think you know, the front part of a car is designed to crumble. When doing a collision, the car is not a rigid body, but during a collision, the front part of the car will slowly crumble. It crumbles of the order of about 100 of a second, or several hundreds of a second. Okay, and in that time scale, during the crumbling, the delta t is also lengthened, and so the forces acting on the car will be smaller, and that will protect the passenger inside the car. If there's a huge force, then it may possibly lead to serious injury or even fatality to the passenger. So that's why we deliberately make the car to crumble, okay, to lengthen the collision time. Now here is a car crash test, is exactly to say. Now you can see how the front part of the car crumble. Now the collision occurs, you see the front part of the car is destroyed, but it does not destroy as a rigid body. It is slowly crumbling. Now, but if the passenger does not wear a seat belt, then due to inertia, his body will be forced to move forward, right? And he will collide with the windshield, and that will be very dangerous for him. Okay. Now this is an effect with an airbag. The airbag simply or the seat belt. You see, the seat belt simply prevent. It provides against a cushion to lengthen the collision time and prevent the passenger from colliding with the windshield or being thrown out of the car. So that's very important for the passenger safety. Okay, so remember to wear a seat belt whenever you ride a car. Okay. Now there are actually two kinds of collision. Okay, we are going to discuss below. Now in a collision, the law of conservation of momentum always applies. When there's no external force acting on the system, or when the external force are negligible compared with the collision force, the law of conservation of momentum always applies. Okay, because when the system is isolated from the environment, or when the system is having a huge collision force, where the other external forces are negligible compared with it, then we can apply the law of conservation of momentum to describe the system. So the initial total momentum of the system will be equal to the total momentum of the system after the collision. Okay, we equate the momentum before and after the collision to get some information about the system. Okay, so the law of conservation of momentum will always hold as long as the external force is negligible. And that is a powerful law in determining the result of a collision. Now, although we are not able to solve the whole dynamic of the problem, we do not know how the velocity changes with time exactly and precisely. We cannot solve it because it's too complicated. The force profile may be changing very complicated, very rapidly, so we cannot do the exact calculation for at every instant. But still, we will be able to predict the outcome of the collision by using the conservation of linear momentum. Now, whether energy is conserved is another matter. Okay, the momentum is always conserved, but not the energy. For an elastic collision, the total energy is conserved. That means the total energy, kinetic energy before the collision, is equal to the total energy of the particle after the collision. That's called an elastic collision. And elastic collision, like a frictionless plane, it is only an idealization. It never exists in the real world. When you have collision, there's always some energy loss. Okay, but if you consider idealized case where there's no energy loss, then you have an elastic collision. And elastic collision is the approximation in some of the situation is a good approximation. For example, colliding between two billiard ball, that is almost an elastic collision. Or you have a super bound ball, then that's all again when you bounce off from the ground, it's almost an elastic collision. But on the other hand, an elastic collision is the collision where the total kinetic energy is not conserved. So the initial total kinetic energy is larger than the final total kinetic energy, since some of the energy has been changed to other form. Like for example, internal energy, which is essentially heat, and also maybe sound. Okay. Now the greatest loss occurs if the bodies move together after collision. If the two bodies stick together after the collision, they move together after collision, then I call this collision a complete inelastic collision. Now, not the word complete. When I say an elastic collision, I only mean the energy loss. But when I say a complete inelastic collision, that means the two bodies stick together. They move together after the collision. Okay. Now let's consider a head-on collision between two bodies. We assume it to occur on a frictional spring. And initially, the mass M1 is moving with velocity u. The mass M2 is at rest. And after the collision, M1 and M2, they move with velocity v1 and v2 respectively. So let's see what will happen. Now, the total linear momentum is always conserved. Okay, provided that no external force, no friction, then I would have the initial momentum equal to m1u be equal to the final momentum. The final total momentum is the sum of the individual momentum of the two particles. So that is m1v1 plus m2v2. Initially, I only have one particle moving, so I only have one m1u, but finally I have two particles moving. So for each of the particle, it has a momentum. So the final total momentum is sum of the two. Okay, but I also know that if that is a complete inelastic collision, suppose for the first case, I study a complete inelastic collision. And so a complete inelastic collision means they move together, right? So they have the same speed after the collision. In that case, V1 and V2 are both equal to V. Okay, so when I put V1 and V2 both equal to V, I will be able to solve for V. V is equal to M1 divided by M1 plus M2 multiplied by U. Okay, so this problem can be solved easily. Okay, if I know that they stick together, then two equations will give you the answer. Now I study a more difficult situation now. I assume that the collision is elastic. Okay, that means kinetic energy is also conserved. Of course, I have the first equation for the total linear momentum. This equation still holds, right? Because momentum is always conserved. Whenever you hear about collision, I think you can write down the momentum conservation equation immediately because collision in most of the situation, the other forces are negligible. So that means momentum conserved. But for the idealized case of the energy conservation, we can write down the conservation of mechanical energy equation. The initial mechanical energy is half m1u1 u square, the kinetic energy particle 1. And here are the two kinetic energy of the two particles after the collision. So namely, they are half m1v1 square and half m2v2 square. So now we have two equations that allow us to solve for v1 and v2. Okay, we have two unknowns, the final velocity of the two particles. Okay. Now, but the equation is a little bit scary. The first equation is linear in v1 and v2. In each term, it contains either v1, v2, or constant. But for the second equation, it is quadratic in v1 and v2. You have v1 square and v2 square. So it's not that easy to solve, right? You can always eliminate one of the variable. but that results in a quadratic equation, which is not so easy to solve. Now we have a trick that allows you to know the result rather easily. You don't necessarily follow this trick, but it only allows you to solve the equation more easily. Now we play around with equation 1. Okay. Let us move the term m1v1 to the left-hand side and divide the whole equation by m1. Okay. Now move this term to the left-hand side and divide the equation by m1. So the left-hand side becomes u minus v1. The right-hand side now becomes m2 over m1 v2. And let me call this equation equation 3. Okay. Now we do the same thing for equation 2 now. Remove the kinetic energy terms, the final kinetic energy terms of the particle 1 to the left-hand side. And then we divide the whole equation by half m1. Okay. So on the left-hand side, I only have u squared minus v1 squared. The half m1 has gone. And on the right-hand side, I now have m2 over m1 v2 squared. Okay. Now we know from elementary algebra that u squared minus v1 squared is equal to u minus v1 times u plus v1. So we just expand this bracket into u minus v1 plus times u plus v1. But we already have u minus v1 in equation 3, right? We already have this. So we can replace this u minus v1 with m2 over m1 v2. We can just replace it with this term. But as soon as we do this, we notice that the m2 over m1, they cancel on both sides. And also, one of the v2, now the right-hand side has a v2 square, while the left-hand side has only one v2. So one of the v2 also cancel. Okay, the result is that we are left with a simple equation of u plus v1 equal to v2, which is very simple. Okay, and I call it equation 4. Okay, so with equation 4 and equation 3 is here, and equation 4 is here, I can easily solve for v2. Let's add equation 4 to equation 2. Okay, when I add equation 4 to equation 2, I can easily see that the v1 will cancel because one is plus and the other is minus. So now I have 2u equal to 1 plus m2 over m1 multiplied by v2. And so v2 is given by this. Okay, and I can easily use equation 4 again to find out v1. v1 is v2 minus u. So v2 is given by this. So I just substitute v2 here, and after some algebra, I got v1. Okay, so that's how I find v1 and v2. Now, so that is the result. These are the results. Now, when we do a calculation, it is important for us to check whether our answer is reasonable. Okay, for some limiting situation. Now, the answer is reasonable for some limiting case does not mean that our answer is correct. But if you find that your answer does not make sense for those limiting case, then you might have make some error in your calculation, and you need to revisit your calculation to check for error. Okay. Now let's see if this two expression applies to some special situation to produce the expected result. Now, first suppose M1 is much larger than M2. So what we are saying is, initially we have a large ball, a very massive ball, moving and colliding with a ball at rest, a small ball at rest. And that corresponds to what situation? We imagine a bowling ball moving with an initial velocity u, colliding with a ping pong ball at rest. So M1, the mass of the bowling ball, is much larger than M2, the mass of the ping pong ball. That is a situation. So what would you expect? Can you tell me What will you expect from this situation? You just learn from your experience, okay? You know from experience what will happen. The bowling ball will not be affected because the bowling ball has such a small mass, right? It will not, the collision will not affect the motion of the bowling ball, right? And the bowling ball will bounce off, okay? And let's see the result. Now look at the equation. Look at this equation. If M1 is much larger than M2, then I can neglect the M2 in both the numerator and the denominator. Is that right? So it becomes M1 divided by M1, which is 1. So V1 will become U. And that means the bowling ball is not affected, right? And this is expected because the bowling ball is much heavier than the bowling ball. It will not be affected by colliding with the bowling ball, right? And that's our expectation. So what is V2? With what velocity will the bowling ball bounce off? I can check this equation, right? When M1 is much larger than M2, M2 can be neglected in the denominator. So it becomes 2M1 divided by M1, which is 2. So V2 is equal to 2U. So the bowling ball will bounce off with twice the initial velocity of the bowling ball. Okay, it does not bounce off with U, velocity U, but bounce off with velocity 2 times the U. Okay, now this is quite unexpected, but I will let you see why in the next slide. Okay, but intuitively you can understand why, because the bowling ball is so massive, so it collides with the bowling ball bounces off with a high velocity. Okay. Now let's consider another special situation. I assume that now M1 is much smaller than M2. And this situation corresponds to the ping pong ball colliding with a bowling ball. Okay. So in that situation, I neglect M1, this two M1 compared with M2, right? And so I get V1 equal to minus U. When I neglect the two M1 here, it becomes minus M2 over M2, which produces a minus 1, a factor of minus 1. So we become V1 equal to minus U. And that means the bowling ball will bounce back. Because of the minus sign, the velocity change sign without changing in magnitude. The bowling ball simply bounces back with the same velocity. Okay, and that's exactly what happens when you throw a bowling ball towards a wall, which is not moved by the bowling ball, right, during the collision. Okay, and in this case, the bowling ball is so heavy, the bowling ball can't affect it. It acts like a fixed wall and allows the bowling ball to simply rebound. Okay, and of course, the bowling ball will not move. And that is apparent from the second equation. When M2 is much larger than M1, this becomes 0. So V2 becomes 0. Okay. Now let's look at the question a little bit deeper. We do not understand why, in the case of when M1 is much larger than M2, why is the bowling ball bounce off with twice the velocity? Why is this so? Let us try to understand that from another point of view. Now we look at the collision from the point of view of an observer who is at rest on the ground. According to this observer, the bowling ball is initially traveling with a velocity U. Now how about looking at this matter, looking at this collision from another point of view? Suppose I have an N sitting on the bowling ball. Okay, so relative to me, sitting on a bowling ball, I will see the bowling ball at rest, right? And the bowling ball is moving towards me with the velocity minus U. So it happens relative to the observer on the bowling ball that the bowling ball will simply bounce off, right? With the same speed. Okay, the velocity just change sign. So eventually, the N will see the bowling ball bounce off with the same speed U. The velocity just change sign. It's just changed from this direction to this direction, right? This is what we expected, and the bowling ball is not affected. Now you notice that in this two reference frame, the velocity are just connected by simply adding a U. When I add a velocity U to the right to every of this ball, then I will go back to the initial reference frame. the reference frame in which the observer is at rest on the ground. So when I add the velocity u on each of the ball, I go back to the original reference frame. So that means in this situation, I can add a velocity u to each of the ball, and I will go back to the inertial reference frame where the observer is at rest on the ground, right? So the bowling ball at rest, when I add u, it becomes u. The ping pong ball is going with velocity u in this reference frame. So when I add another velocity u, it becomes 2u, right? So that's why the person at rest on the ground will see the ping pong ball bounce off as 2u. And that's exactly what is happening here. Okay. Now, so looking at the same collision from 2 points of view allows you to understand something. Okay. And the important thing that allows us to do so is that there's no real distinction between being at rest and in uniform motion. So you can describe the physical reality with respect to either an observer at rest on the ground or an observer who is at rest on the bowling ball. They both give the same description. And the velocity between the two frames of reference are simply related by a transformation, which amounts to addition of the velocity u. Okay. So I hope this will give you some insight, but I will not test you in or change in frame versus frame in the exam. Don't worry about that. Now let's see this video. Sorry. I should share. I should share this with. Sorry about that. I should share this with the sound on, and optimize the video. I go back. I go back a little bit. Can you hear the sound now?
Check out how high these different balls bounce. The basketball, the super bouncy ball, and the golf ball. Now I'm gonna try the golf ball on top of the bouncy ball, on top of the basketball. And
Sorry.
then I'm gonna explain how it's related to a supernova. Did you see that? Probably not. So here it is again. The golf ball bounced to 28 feet. We dropped it from about 3.5 feet, so it went up 800% of its dropped height. In fact, if you consider that by itself, the golf ball bounces about 70% of its dropped height. It went as high as if it had fallen from 40 feet up. That is awesome. So how can we get the golf ball to bounce up with that much energy? Let's simplify it to these two balls. When you drop them individually, each ball starts out with some potential energy from the height of the drop. As the balls hit the ground, some energy goes into heating up the ground and some goes into heating the ball. Because that energy left the ball system, you can't get back up to the same height. But when you combine them, the tennis ball goes higher than its dropped height. Way higher. Where does it get the extra energy? As the basketball bounces, it compresses, storing elastic potential energy. As it releases, it springboards the tennis ball upward just at the right moment. This is like the double bounce on a trampoline when you jump right before someone else. You prepare the elastic of the trampoline by stretching it and storing energy, which can then bounce the jumper even higher. In the same way, the basketball stores energy in its compression and is able to push the tennis ball. But just like the double bounce preparer, the basketball can't go as high. You can see that here. It bounces even less when 3 balls are dropped together. Also, during that transfer of energy, some momentum transfers from the basketball to the tennis ball. And since the basketball starts with way more momentum because of its larger mass, the tennis ball's velocity increases by a lot, and it flies up, and away. Now back to the triple super ball bounce. Now you get the energy from the basketball's bounce being transferred into the bounce of the super bouncy ball, which is then transferred to the golf ball's bounce. You put the same amount of energy or momentum from 2 more massive objects into a smaller object, and it will go much faster. Epic! Just like the explosions of a supernova, which may seem unrelated, but what we just did is analogous to the process that occurs during the explosion of a supernova. Just like our more massive basketball transfers momentum to the smaller balls, energy from the dense core of the supernova supernova is transferred in a shock wave that moves through the star to the less dense layers and accelerates them outward at a super high velocity. More massive or denser layers in the core of the supernova begin to collapse when fusion stops there. The collapse is halted when the neutrons in the core actually touch, sort of. This causes the implosion to rebound and bounce outward. You end up with a dense core left behind and these wild outer shells of star exploding outward. Pretty cool. And of course, if you try this at home, which you should, you have to make sure the balls are perfectly vertically aligned because any off-centeredness gets amplified by the 2 points of contact, which is why we sadly couldn't get the quadruple tower of balls to work. But if you put a little ring of hot glue or something similar on the balls, it helps to balance them. Happy physicsing!
All right, so this is a physics girl video. Okay, you can find her in the YouTube channel. She's a very famous physicist popularizing physics. Now, I actually have the same. I actually have the same toy. This is the same toy. This is called the Astro Blaster, which is essentially a smaller version of what she did on the TV. But I would not be able to show you this because when I try to drop this, the upper ball will be bounced to at least the height of the ceiling, which I cannot include it in this and I cannot include it in my camera. My camera is not so wide to show you the bouncing effect, so I'm not able to show you the real thing here in the Zoom section. Now, but the important thing is when the large ball hit the ground, okay, it bounced back, right? Assuming elastic collision, it almost have a zero change in energy, so it bounced back with the same speed. But then it will collide with the smaller ball on the top, and the momentum will be transferred from the large ball one by one to the balls at the top, which are much smaller in mass. And so eventually the same momentum transfer upwards, the smaller mass will get the higher speed, right? And so that's why the smallest ball at the top will be ejected at a high speed, okay? And that goes maybe 1 or 2 story heights, okay? That effect is really amazing. But I'm not able to show you now because we are not in the real classroom, okay? Now, in the homework, we will have a simplified situation. I will ask you to calculate the effect, the bouncing effect of 2 balls, and you will find that the smaller ball will reach a height which is about 9 times the initial height of drop. So when you drop the 2 balls at a height of 10 cm of the ground, then the smaller ball at the top will reach a height of 90 cm above the ground level, which is pretty amazing. I will let you solve this problem. It only amounts to applying the change in momentum one by one to the collision. Okay. Now also there is another interesting effect. I don't know whether you play snooker. When I was at your age, I played snooker quite a lot. And in playing snooker, there's a kind of collision called head-on collision. When I hit the white ball with a cube, and when the white ball collide head-on with the red ball simply moves off with the same speed as the white ball. Okay. Now this can be derived from the previous equation. Now look at the previous equation. Now, if M1 and M2 are equal, if the balls have the same mass, if both the white ball and the red ball are the same mass, then V1 will be 0. And V2, because M1 and M2 are equal, V2 will simply be equal to U, right? So that means if the 2 balls have the same mass and they collide elastically, then the ball, which is initially at rest, will then move off with the same speed at the at the ball that is colliding with it. Okay, and the ball that is originally moving will stop at rest after the collision. Okay, so that means after the collision, the white ball will remain still, okay, at that position. And the red ball will essentially be moving off at the same velocity as the initial velocity of the white ball. Okay, so that is called a stun. A stun means the white ball remain at rest after the collision. It comes to rest after the collision, while the red ball move off with the same initial velocity as the white ball. Okay, so that is the snooker trick. Now let's take a break for 10 minutes. Now here we have two balls. Okay, they look the same, right? They look like to be made of the same material. Okay, but let's see what will happen when they fall down to the table. Let's see. Now, obviously, this ball is more bouncing, right, than this one. When this ball drops to the ground, to the table, it bounce back to a certain height. While for this ball, when I drop it to the table, it simply stays there without bouncing back. So these two balls actually make of different materials. They are chemically different, right? And this ball is designed to be more bouncing. Okay, so it is more like an elastic collision, while this ball is more like an inelastic collision. Okay, it is designed to not bounce. Okay, so it dissipates all the energy in the chemical bond, in the vibration of chemical bond as heat. So it loses all the energy after bouncing with the table. Okay, so here is a different. Okay, so here is a interesting toy to show you. Let's go back. And let's proceed with a so-called upright collision. Upright collision is a bit more difficult. That's it. Let me share the screen. Upright collision is a little bit more difficult. We consider two particles colliding at an angle. Okay. For simplicity, we assume the two bodies to be of the same mass and they collide elastically. Just that the collision does not happen on a straight line. The two balls bounce off at a certain angle. We assume the ball 1 and the ball 2, they bounce off, making an angle theta and phi with the initial direction. I call the initial direction x. Okay, so theta and phi are the direction of the final direction of the ball making with the initial direction, the angle that the final direction makes with the initial direction. Okay, and the final velocity are v1 and v2. Okay, now we set up a coordinate like this. X is an initial direction of this ball, okay, and y is a direction that is perpendicular to this direction. Now let's apply the conservation of linear momentum. Now because well the collision is two-dimensional, it involves x and the y direction. So if we want to write out the momentum conservation equation, we have to write out the conservation equation respectively in two components. The first equation would be for the x component. We resolve all the velocity along the x component. We multiply them with the mass and then sum them up to get the initial and the final momentum along that direction. So initially the ball is the first ball is moving to the right, so it's the x direction. So you have mu here. For the final velocity of the two balls, they are making an angle theta and phi with the x direction. So you have mv1 and mv2, but you have to resolve it along the x direction. That means you have to multiply by cosine theta and cosine phi. Okay, so mv1 cosine theta plus mv2 cosine phi will give you the sum of the momentum component in the x direction. Okay, how about the y direction? Well, we just resolve the velocity along the y direction. For this mass 1, the y component of the velocity is mv1 sine theta, and for the mass 2, the y component of the momentum is mv2 sine phi. Now, the two y component of the momentum, they're opposite. But since there's no initial y component of the momentum, the initial y component of the momentum is 0. So the final total y component of the momentum must also be 0. And that means the magnitude of the two y components are equal. So that means mv1 sine theta is equal to mv2 sine phi. Okay, so this is the second equation. And of course, we have the energy conservation equation because we assume the total kinetic energy being conserved. Okay, so we have this equation as before. Okay. Now, how to solve it? It looks scary because all the particles have the same mass. The two particles have the same mass. We can solve. We can eliminate the m on both sides, and so that becomes a free equation like this. This is for the x component of momentum. This is y component of momentum. This is an energy equation. Okay. Now, this equation looks a little bit scary. Before solving it, let us look at it in more detail. How many unknowns are there? We know the initial velocity, right? But we don't know the final velocity, v1 and v2. And we also don't know the angle, theta and phi. So there are totally 4 unknowns, right? v1, v2, theta, and phi. There are totally 4 unknowns. But there only are 3 equations. You cannot have 3 equations solving for 4 unknowns. That means you do not have enough equation to solve for all of them. Now, one of the, there are some information missing. There are some information missing. And that probably come from, here. We do not know the angle between the line joining the center of the two spheres, how this line makes an angle with the initial direction. We don't know that angle. That's probably the missing information. Now, but at the time being, we don't want to specify this information further. But as long as we have 3 equations, we can always solve 3 of the variable in terms of the other one. Okay, we can know some information about this. Even if we cannot solve all the unknown, we can express some of the variable in terms of the others. And let's see what we can arrive after solving this system of equation. Now we first work with the first equation. We move the term v1 cosine theta to the left hand side, and we take the square of both sides. Okay, so it becomes v2 square cosine square phi, and on the left we have u minus v1 cosine square, u minus v1 cosine theta complete square. And so you got 3 terms. A minus b square is a square plus b square minus 2ab. So we now apply it to here. We have u square plus v1 square cosine square theta minus 2u v1 cosine theta is simply a plus minus b square equal to a square plus b square minus 2ab. A simple application of the algebra we learned in high school, right? And we square the both sides of the second equation. It becomes v2 square sine square phi equal to v1 square sine square theta. Now, why do we do this? Because we notice that if we add up these 2 equations after squaring, we will be able to get rid of the phi. Because we know that cosine square phi plus sine square phi is equal to 1. And that means when we add up 2 equations, the phi will gone. Okay, so that's exactly what we are going to do. And after adding the left-hand side, we got v2 square. And how about the right-hand side? when we add the right-hand side of the two equations, we have V1 cosine square theta plus V1 square sine square theta. So cosine square theta plus sine square theta is again 1. So we have V1 square, simply V1 square on the right-hand side. Of course, we have the U square, and we have this term also, minus 2U V1 cosine theta. Okay. So let me call this equation 4. And since now I have the square, right? I have the square with the V, right? So I can add equation 4 to equation 3. When I do this, I find that the V2 square have cancelled on both sides. And also the U square, they also cancel on both sides. Okay. So that means when I add up the two equations, the left-hand side becomes 0. Because the U square and the V square, they both cancel on both sides of the equation. So on the left-hand side, I'm left with 0. And the right-hand side, I simply have 2 of V1 square. This two V1 square added together. And I also have this term, minus 2U V1 cosine theta. And when I take out a factor of V1, obviously V1 is not 0. So the factor of 2 is also unimportant. So what I got is V1 equal to U cosine theta. Okay, because the only possibility for this equation to satisfy is V1 equal to U cosine theta. Okay, so I now find, at least I find V1 in terms of one of the angle theta. Okay, this angle is also unknown, but I know the magnitude of V1 in terms of the angle theta. Now, having find V1, we now put the V1 back to this equation and solve for V2. So V2 is square root U square minus V1 square. And V1 is simply U square cosine square theta. V1 square is simply U square cosine square theta. So I now have 1 minus cosine square theta, which gives me the sine square. And I take the square root. So I got U sine theta as V2. Okay, so I obtain both V1 and V2 in terms of theta. Now from equation 2, I have this equation, V1 sine theta minus V2 sine phi equal to 0. But I already have found V1 and V2, right? V1 is U cosine theta, while V2 is U sine theta, right? And after substituting these two for V1 and V2, I find that there's a common factor of sine theta and U, which which can be taken out. And what is left inside the bracket is cosine theta minus sine phi. And since sine theta is larger than 0, I know that this is a positive angle. So the only possibility for this equation to satisfy is cosine theta equal to sine phi. But as I know, sine phi is equal to cosine 90 degrees minus phi, right? So when two cosine are being equal and both angles are equal, we know that theta is equal to 90 degrees minus phi, or in other words, theta plus phi is equal to 90 degrees. Okay. And that means what? That means this angle, theta plus phi, is equal to the right angle. And that means what? That means the two balls, they will move up at right angle. Okay. This is a very interesting result when the two balls have the same mass and the two balls are colliding elastically. This is a very special result. Okay. The two balls move off at the right angle. Okay. Now, but we can obtain the same result by using vectors. You will find it more easy, but with doing it by using vectors. Now we can just write out the vector equation for the momentum conservation. If I use a vector sign, U1 vector, V1 vector, and V2 vector here, I already represent the two directions. I don't need to write out the components. So when I write U vector equal to V1 vector plus V2 vector, I already have included these two equations. I do not need to do the projection. Okay. The energy equation is of course the same. The energy equation is of course U square V1 square plus V2 square. All the M has been canceled on both sides, right? Now here comes the trick. I form a dot product of equation 1 with itself. Now let me write it more carefully to allow you understand what is happening. I square this equation, and what I mean by square is actually forming a dot product of the vector with itself. So on the left-hand side, I have u dot u, and on the right-hand side, I have v1 plus v2, forming a dot product with itself with v1 plus v2. Now u dot u is of course u squared, the square of the magnitude. And how about this? v1 dot v1 is of course v1 square. v2 dot v2 is of course v2 square, but we have two cross terms. The two cross term is v1 dot v2 and v2 dot v1. But we know that the dot product is commutative, and that means v1 dot v2 is equal to v2 dot v1. So we have 2 times v1 dot v2. Now notice that there's a dot here. We are talking about the dot product. Okay, the dot product has an angle. Okay, you have to include a cosine, the angle between the two vectors. So don't ignore this. Okay, if you ignore this, you will get a wrong answer. The dot product means that you have to include the cosine, the angle between the two vectors in the result. Okay, now so we arrive at this equation. Okay, now but when we compare this equation with the second equation, u squared the same, v1 squared plus v2 is the same, right? And that means what? That means v1 plus v1 dot v2 must be equal to 0. Otherwise, the both equations cannot be satisfied. Okay, when you find a difference between this equation and this equation, you just find v1 dot v2 being equal to 0. And that means what? That means v1 and v2 are perpendicular to each other. Now you don't need to do the complicated calculation. This equation dot product, the dot product of two vectors being 0, where v1 and v2 themselves are not 0, it already means they are perpendicular to each other. So you got this result. The two velocities are making a right angle with each other. Okay. And if v1 and v2 makes a right angle, this is the vector equation. Now u is the original vector. This is u, right? The equations say u is equal to v1 plus v2. So I draw a vector diagram. This is v1, this is v2. And when v1 plus v2 is equal to u, the three vectors will form such a triangle. Is that right? v1 plus v2 is equal to u, right? And since the angle between v1 and v2 is a right angle, right? So this is a right angle triangle. And so now you can easily solve v1 and v2 in terms of theta. v1 is simply u cosine theta, while v2 is simply u sine theta. Okay, so you now have the two results. Okay, now you can see the result is the calculation is very elegant. It does not require you to resolve the component. All the resolution of the component is hidden in the dot product. You can simply form a dot product of the vector equation with itself to obtain the result that the two velocities are perpendicular to each other. Okay, so that's the advantage of using vector in your calculation. Okay. Now this is a very famous result. If you hit the red ball with a white ball at an angle, then if you do it fast enough, the two balls will move off as about almost a right angle. Okay, this is approximate elastic collision. If friction and spin and rotation of the ball can be neglected, they come out to be a almost 90-degree scattering. I show you this video. How do I share this video? I go back. Okay, let's do it once more. Hopefully I can do it now. I am sorry that this video is in Cantonese, but I'm sure you can understand most of the things just by looking at it.
嗱，不如我哋試下用呢隻氣剪飛碟嚟到示範一啲碰撞。
This is a disc which can be levitated above the
就咁
table
推嘅時候咧，因為佢同台之間嘅摩擦力好大啊，所以佢咧就好快停咗。咁但係我着咗個氣剪嘅時候咧，情況就唔同啦。
There's some air coming out from the disc, so it levitated the disc above the table, minimizing the
頭
friction.
先見到啲咩？因為着嗰個氣剪嘅時候咧，有啲氣噴出嚟啦，懸浮咗佢，咁就令到佢咧差唔多咧喺冇摩擦力底下咧。向前咁運動，咁根據牛頓第一定律咧，佢已經用一個均勻嘅速度咧向前運動嘅。咁我可以咧用呢兩個氣墊咧嚟示範一啲碰撞啦。嗱，第一個碰撞咧，我哋試下一個正面嘅彈性碰撞先啦。咁呢邊呢隻氣墊咧，
係令到佢
唔喐先嘅。而我推一推右手邊呢隻氣墊，就令到佢咧同原來
Initially the ball the disc come
本來衝埋去嗰隻氣墊咧撞完之後咧就唔喐喎。調翻轉，本來唔喐嗰隻氣墊咧，撞完之後咧，就以差唔多係開始嘅時候呢隻氣墊嘅速度咧，就飛走咗。嗱，或者我哋試下一個斜角碰撞啦。呢隻氣墊係唔喐嘅，另外一隻氣墊咧就撞埋去，但係唔係撞到正喎，係有個角度嘅。兩隻氣墊咧係用唔同方向咧飛走咗嘅。大家細心啲睇一睇個角度嘅時候咧，大家會發覺碰撞完之後，兩隻氣墊之間嘅夾角咧係差唔多係一個直角嚟嘅。
Okay, so that's a simple illustration of a bright collision. Okay, and now here we have a checkpoint for you. Okay, now we consider the case of energy loss, and we assume the energy loss to be delta E. Now to make the quantity positive, I define the delta E is a change in energy, which takes the negative value, right? Because the final energy is smaller than the initial energy. But let us consider the absolute magnitude of it. So this quantity must be positive. I would like you to show that the angle between the two balls after the collision, the angle alpha, cosine alpha is equal to absolute delta E divided by m v1 v2. I want you to show this result. The hint is that you make use of the weighted equation and the dot product, but you include the energy loss. That is a trick. Now, I just want you to try yourself. I give you a hint. You can apply the momentum equation as before. Momentum is always conserved. So you now have mu vector equal to mv1 plus mv2, right? You can cancel the m on both sides, right? But how about the energy? The energy equation says so. The initial energy is equal to the final energy. But wait, we now have energy loss. How to include this energy loss in the energy equation? Can somebody answer me? Where do you add this term? If this is an energy loss? Come on, try. Type something in the chat box. Hey, I've got the answer from you. But the energy loss is due to the collision, not friction. Okay. In the collision, some energy is changed to heat. Okay, not friction. I just want you to, if I know this is the energy loss in the collision, then how do I include this term in the equation of conservation of energy? Now, if kinetic energy conserved, I have this equation, right? How do I modify this? Yeah, sure. You are correct. Yeah, you are correct. You add this term to the right side of the equation. Sorry again. Now, because of the energy loss, the initial kinetic energy is larger than the final energy, right? So this term is larger than this term. And what are the difference? The differences goes to heat. And this is the term that represents the energy goes to heat, right? So the final kinetic energy plus the heat is equal to the initial energy. Okay. Now, can you use this relationship, these two equations, to show this result? Just a few steps. You try doing this. You just do the same thing as what I did. You just form a dot product of the first equation itself, and you make use of the second equation. Have you got the answer? Let's do it together. Now, let's square the first equation as before. So this equation becomes u square equal to what? v1 square plus v2 square plus 2v1 dot v2. We are essentially forming a dot product of the equation with itself, right? And how about the second equation? Now let's divide the whole equation by half m. And that means I have u square equal to what? Equal to v1 square plus v2 square plus what? Plus 2 delta E divided by m. Is that right? I just divide the second equation with half m, right? And that's the answer. Now you can easily see that when I compare the two equations, that means the last term must be equal, right? The front part of the equation are identical. That means the last term must be equal to each other. And what I mean by v1 dot v2 is what? Is v1 multiplied by v2 cosine the angle between them. The angle is alpha, right? This is v1, this is v2. The dot product has a definition that the dot product is equal to the magnitude of the vector multiplied together, multiplied by the cosine the angle between them. Okay, this is the definition of the dot product. And it's equal to what? Equal to here, we have delta E divided by M. Okay, so the result follows. This result follows. Okay. Now, what is the meaning of this result? We know that, we know that delta E is always positive. Yes. Yeah, sure. You got the answer. Yeah. Now, you notice that since delta E is always positive because of the absolute sign, you have cosine alpha being positive, right? So the equation means you have cosine, you have cosine alpha being positive. And that means alpha, what? alpha is more than power 2, is more than 90 degrees, right? And so this angle is always more than 90 degrees. It cannot be larger than 90 degrees. Whenever there's energy loss, two identical particles after collision, they will move off at an angle that is smaller than the right angle. They will move off at an acute angle. Okay, they cannot move off by an angle larger than 90 degrees. That is the result dictated by the conservation of energy. Okay. Now let's talk a little bit about the center of mass concept before letting you go. Now, in the beginning of our discussion, we prove Newton's second law for a system particle, right? We have shown you that when external forces are applied to the system, then external force will be equal to the rate of change of the total linear momentum of the system, where the total linear momentum is a sum of the individual momentum of the particle. So we write the capital P as summation small pi, where pi is the linear momentum of the I particle. And we form a sum of I from 1 to n, meaning that we include the momentum from all particles. Okay. Now, but we know that the small pi can be written as MIVI, where MI is of course the mass of the I particle and VI is the velocity of the I particle, right? So I just write P in terms of MV. Now, but I can further transform this equation by writing the velocity in terms of the time derivative of the position. So I write VI as the RI dt, where RI is the position vector of the I particle. So I further change this V into dr dt. Okay. Is that okay for you? Now let's see the magic. I can take this derivative out of the summation because the m are constant. Okay, and the derivative is a linear operation. That means if each of the term contain a derivative, I can always move the derivative out of the summation, out of the bracket. Okay, and so it becomes the second derivative of this quantity, the second time derivative of summation MIRI. Now notice that MRI is a vector. It denotes the position of the I particle. Okay. Now let's play a trick. We know that the total mass of the system is equal to the sum of the mass of the individual particle. So the total mass M is summation of Mi. Okay, that is the sum of the mass of the particle. That's M1 plus M2 up to Mn is capital M. We divide this summation by the total mass of the system, and we multiply on the outside the mass of the total mass of the system. So the M cancel. We are doing nothing. Okay, we just add the M, add the M here and divide the M. Okay. Now, but it is interesting to look at the yellow box. Okay, I define the yellow box to be a position vector, which I call R. This vector is the vector of the center of mass. Okay, I define this vector to be a vector to specify the position R of the center of mass. Okay. Now, this is a definition, but how do I know that this is a position vector? I can look at the dimension. Okay. Now, in the summation, the mass is multiplied by the distance. The R vector carry a dimension of length, right? So in the summation, I have the dimension of mass multiplied by the dimension of length. But then I divide by the total mass, which carry a dimension of mass. So the yellow box now carry a dimension of length, which is a position vector, right? I can always define this vector by capital R. Okay, R is by definition this guy. Okay, and if I do so, I will arrive at Newton's second law for a system of particles in a very interesting form. I can write capital F equal to total mass of the system multiplied by the second derivative of capital R respect to time, which is acceleration, right? The second derivative of a position with respect to time in an acceleration. But it's an acceleration of what? Acceleration of not a single point mass. It's an acceleration of the center of mass of the system. So now by defining this quantity to be the center of mass position, I find that Newton's law can be written in a form that expresses the total force acting on the system and also related to the acceleration of the center of mass. So the center of mass plays a role just like a single particle, right? If you replace a single particle mass with the total mass of the system, if you replace a single mass acceleration with now the acceleration of the center of mass, you reproduce the Newton's second law for a system particle. Now that is an amazing trick. Okay, that is an amazing trick. You can now describe everything in terms of the center of mass, just like you are handling a single particle. Okay, but how do we find the center of mass? What is the center of mass actually? Now, if you I don't know if your high school teacher have shown you this. This is a so-called balancing bird. It's an extended body, but it somehow can be balanced. The whole bird can be balanced at the position of the mouse. You can use a single finger to balance it at the position of the mouth. Okay. Now, so for this bird, the center of mass position is exactly below the mouth of the bird. So you can stably apply an upward force to balance the downward force of gravity. The center of mass of a body is actually the point through which the whole mass of the body is concentrated at. The whole mass of the body simply be concentrated at that point. Okay, and that's called the center of mass position. Now, how about this equation? What does this equation mean? If I now apply the Newton's second law to the center of mass, I have this equation. This already proved, right? So how to interpret this? Now, suppose you have a hammer, a complicated object. Okay, a hammer is a solid object with a very complicated shape. But somehow by balancing it, you try different point, you will find the center of mass. The center of mass is somewhere near the head of the hammer because the head of the hammer is much heavier than the handle. So the mass of the center of mass of the hammer is somewhere here. Now I throw it. And the equations tell us what? It tells us that as long as you trace the position of the center of mass, then the acceleration of the center of mass will simply follow Newton's law in the usual form. Okay, so you have the mass multiplied by the acceleration of the center of mass. It must be equal to the net force acting on the hammer. And the only net force in this situation is the downward force of gravity, right? So that means what? That means the center of mass behaves like a single particle. It undergoes a projectile motion under gravity. And so when you trace the position of the center of mass, it simply follows a simple projectile motion, just like what you did with a single particle. Okay, so no matter how the hammer moves, it may be moving in a very complicated manner because there's a rotation, right? When you throw a hammer, the hammer may rotate very complicatedly in the sky. But when you trace the center of mass position, when you trace the position of the center of mass at every instant, and you join them up, you will find that it follows the Newton's second law, just like a single particle. And the motion is simply a projectile motion under gravity. That is an amazing thing, right? Now, even we don't know how to deal with rotation, we obtain some useful information about the motion of the body. At least we know that the center of mass will follow a simple projectile motion. That is quite amazing, right? Now, the MIT Department of Physics, they have such a demonstration. They throw a rigid body, a large body, okay? When they throw it with all the light ons, you cannot see the center of mass, right? But they turn off all the light and they put a small light bulb or maybe a small LED at the position of the center of mass. If they do so and throw it in the dark, you will find that the position of center of mass follow exactly a projectile motion. It will not jiggle around in air. But if you place a light bulb in a position that is not exactly the center of mass, you off the center of mass, then you will find that you turn off the light, that point will jiggle around because that point does not follow a simple projectile motion. Now let's see the demonstration. It's quite interesting. I better share the screen with you with the screen optimized for video. And here we are. Now we throw the object, we toss the object under bright light. Now the red dot is the center of mass position, okay? Now we paint orange the position of the center of mass. Let's see, this is a, now you see the center of mass follows a projectile motion, right? It's a simple projectile motion. You do not see the rotation now, right? But how about this guy? The center of the object, this is not a uniform disk. The center of the object does not correspond to the center of mass of the object. Now, if we locate the center of mass, that follows a simple projectile motion. Now let's go back a little bit. Now for this object, now we have an bright point located at the center of the object, but the object here, the circular disk here, is not uniform. It is heavier on one side than on other. So when the guy throws this object, they find that this point will jiggle around because it is not the center of mass. Now let's see. It's the center of the object, but not the center of mass. So you see, it jiggle around, the point jiggle around, right? But if I do it, if I now label the position of the center of mass exactly and throw it again, it will simply follow a projectile motion. Okay, so that is the difference, the interesting thing. Now, I also have such a demonstration, but unfortunately, I will not be able to show you here because the room is so small and I cannot use my camera to cover all the projectile motion. That's a pity thing. But I hope you understand the idea of center of mass. And in the next lecture, we will go through a more thorough discussion about this concept, including how we formulate Newton's second law in terms of it, and how we calculate it for some complicated shape using integration. We are going to discuss it more in the next lecture. So let's stop here and see you again on next Monday. Okay. So